All right, I'm going to talk about architecture. I've had, over 20 plus years of industry experience in designing routers and switches and building them. I feel over my tenure with small and big organizations that I have been associated with, we did some things really, really well. And I felt some things needed to change with time. What excites me about this architecture and at Arrcus was an opportunity to start from first principles. The net result that we have come up with is an architecture that scales for an operating system, is highly simple and secured. The OS itself is a common OS for routers and switches. It can run one OS, one architecture on routers and switches of various different form factors. And it's a 64-bit OS, scales out. And as I explain you this architecture, my hope is that you'll be both conversant and confident enough in turn to socialize this with your friends and your contacts in your network, yeah? So with that, let's start and dive down into architecture. As it's shown here, everything in white is a bare metal switch or a hardware. Everything in light blue is Linux kernel. Everything in dark blue and green is either a homegrown Arrcus software components or third-party processes that have been heavily modified to fit into this environment. One thing we get with white boxes is good amount of CPU and memory, cheap. CPU these days tend to scale out in terms of number of cores, and therefore you're going to see more and more CPUs come out with more number of cores, which means from a software perspective, if software can exploit those cores, that would be phenomenal. So one of the things we have tried to do that is actually move everything in user space. It's a microservices-based architecture. It gives us two big benefits. If you have a control plane image separated out from kernel, your upgrade stories become relatively very, very simple. More importantly, as you start to upgrade your network software, your HA becomes relatively simple because it reduces the downtime otherwise needed to boot up the entire set of an image. So now you can start to look at technologies like graceful restart because your control plane uptime is significantly reduced on the fixed form factor, and you can actually deploy NSF or graceful restart. It becomes very effective. Like I said, everything is in user space. Each and every component that we have designed, software component, is multi-threaded. Well, when you start to put threads inside a software, you really, really want to keep in mind how you are threading the software components. You do not want to lock the global tables. If you lock the global tables, you sort of lose out on an ability to exploit cores because you're going to be held by a lock. So
I've actually got a question for you on that because I've spent a lot of time on that. I work in the service provider space and specifically the white box space and disaggregated networking. And so we spend a lot of time on this idea of, especially BGP, it's very, very, very difficult for network operating system providers to make multi-threaded and multi-core in the past. So when you have to take in a lot of full tables, that becomes a huge performance bottleneck. How are you solving that challenge? Because that seems to be a universal challenge for NOS vendors.
Yeah, so BGP is a peculiar protocol in sense that if you look at the protocol, most of the functionality that protocol asks you to do is in a pipelining fashion, which means the core functionality is something that you, even if you thread it out, you're going to end up locking the global tables. But there is a functionality around BGP that you can completely thread it out, more like your keep alives when you start talking about session scales, or you build buffers and you want to flush the buffers on the sockets, take them on a separate thread, so forth and so on. So there are ways to scale this out without introducing locks or minimizing the set of locks. And one of the things we've been focused on across each and every component is something along the same lines, right? Actually, to your point, it requires you to have deep protocol expertise to get around to that problem, right?
So would that be maybe can you do it by peer? Or I've seen people do that where by peer will maybe get, so that you're not having to multi-thread the BGP update.
You could. That is what software developers would have done when they designed BGP using Erlang. In olden days, they would have done it completely a threaded model using peer. We aren't using that, but we have used other means to thread it out. Happy to talk to you in details offline. But it's a fully threaded architecture, not just BGP, RIP, FIB, everything has been threaded out. And as a result of that, it allows us to exploit number of cores that are made available to us. And fortunately, with white boxes these days, we get 8-core, 16-core systems, which is just amazing for the routers because it helps us address routing scale that is presented to us today and for the next 10 years to come, right? It's a 64-bit operating systems. So to your point earlier, you asked a question about route reflectors. We can easily scale over 100 million paths. When you talk about scaling, most of the operating systems will talk about their ability to scale at 100 million paths and above. What really matters is how fast do you scale and converge at 100 million paths. And if you can exploit cores in some fashion, then that improves your overall convergence.
So how fast can you converge on that? Because you're right, that really is the trick. Taking in the routes is one thing. Getting convergence and forwarding is another.
I can talk to you offline, but I'll tell you this, that we were compared against one of the open source vendors, and the performance of the convergence rate that the operating system showed was orders of magnitude more. Okay. So it's pretty damn fast. It scales pretty well. I don't think we have numbers today to show, is it?
We don't have numbers.
But we'd be more than happy to share it with you.
Yeah, sure, that'd be great.
Right? It's, again, switch or server agnostic, Intel or ARM agnostic. It can run on any processors. And we wanted to get a couple of key features right as we started the architecture. Of course, the architecture supports IPv4, IPv6 standalone, MPLS, and VXLAN. It's also SR capable. From the northbound perspective, I think somebody had asked the question earlier. From an orchestration standpoint, it supports CLI, REST, and NetConf. But more importantly, it harmonizes them down to a model-driven configuration, which we adopt to OpenConfig. We believe this is going to help reduce the ongoing OpEx cost of our operators because they have already onboarded it. And from our perspective, as we enable new platforms, the changes would be pretty incremental. So we use OpenConfig up here. All the core software modules are OpenConfig capable, and they can actually work with it. So there's no translation layer here. The other thing that we have developed is our own data store, homegrown data store. It's a JSON-based. It uses JSON-based schemas. All the software components connect to that and store their ephemeral data. So we not only store SNMP counters or protocol counters, but we store everything, like I mentioned, BGP paths, routes, next hops, peer changes. Everything's been stored up here. And from there, it connects to our real-time telemetry agent, which uses Kafka to stream it out. It also supports GNMI. We understand that both Kafka and GNMI are sort of religion when it comes to operators. They might have their proprietary transports or new standards-based transports that they would want to support, and the architecture supports that. So it's pretty pluggable in that sense from a transport perspective. And last but not the least, as I mentioned, we wanted the control plane to run on switch as well as routers. When we started this, we could not find any hardware abstraction layer that could help us get to both switch as well as routers. As you may very well know, it's very different when it comes to programming of a switch versus a router. And we needed something that can harmonize it very well. So if you can see, this is our own version of HAL. We call it as a DPAL. It, again, resides in the user space. Everything north to DPAL is a control plane. Everything south to DPAL is a set of plugins. From our perspective, Linux kernel is a plugin. We do not use kernel in the forwarding path at all. One of the biggest benefits of that is programming of a kernel is typically done at a much slower rate than a programming of SDK. SDK typically programs at a way more faster rate. And taking the kernel out of forwarding path just helps us program a lot more faster. More importantly, as we embarked on the routing platforms, you have certain routing capabilities that you don't want probably kernel to do, like backup path supports and so forth and so on. And so just decoupling it helps us make a lot more faster. We also know that if we have to program kernel along with the SDK, kernel typically, like I mentioned, operates at a slower rate. We don't want control plane to react to this. So this layer is responsible to magically take care of it. However way it would take care of it, it should take care of it. It supports, like I said, v4, v6, and MPLS. already, it is also designed to be multi-threaded, particularly if SDK allows you to run in a multi-threaded manner. It can run as a multi-threaded user space daemon. It can run on a fixed form factor or a chassis-based system, and line card or a chassis-based systems. And this is particularly interesting because when I'll talk about it a little bit more when we come to in the later sections where we offload the control plane off the box. The kind of the data that it needs to deal with is any interface-related data, fib-related data, ACL COS that needs to be programmed. And from the chip perspective, it polls the chip to get any counters that it needs or any chip level information, including if you have a BFD-like operation operated at the chip level, at the hardware level, it deals with that as well. Yeah?
So I see you've got Broadcom in there. I'm curious, have you guys done any hardware validation on the Qumran chipset? Because in the world of white box in the carrier space, we're using Qumran quite a bit now.
So we have done so far on the DNX side is the support for J+ and J2s.
Okay.
We're waiting for J2C. That would be our way of supporting Qumran, but we haven't enabled Qumran yet.
Okay.
But architecturally, I mean, it's the same family, so
Sure.
it's an easy port. It's a question of getting use cases like these to figure out the intersection with where we're headed as well as what the requirement is.
Right.
Precisely. Since we think kernel is just a plugin for us at the DPAL layer, we could take everything in the control plane and technically run it on the server and convert the server into a complete layer 3 device for us. The architecture as it's designed and as I talked about, it lends itself very well to DPDK or ODP, where you would need to modify their equivalent of fibs to make sure that the forwarding takes place appropriately. But this helps us get into fabrics where end-to-end fabrics would be layer 3 capable, be it a V4 or V6 fabrics. Because we have embarked on OpenConfig as a orchestration model, we work seamlessly with any cloud-based ODL flavors of the controllers. It just works using netconf and restconf. You could use a controller in the cloud and program one or more switches or routers, no problem at it. Yeah. So we talked about scale. We talked about how the Arrcus is designed to exploit the scale-out behavior of the CPU, how from a memory perspective it scales out. If you look at it, because of our architecture, it's relatively extremely easy for us to decouple the control plane in a manner that you would have the DPAL-like applications reside on a fixed form factor switches or routers and offload the control plane to a high-performance server that would sit next to the fixed form factors. And there could be several reasons to do this. One is if you think your control plane in your network is growing, in some networks we were told that it grows over 20% year over year, then this is an easier approach where you can run the control plane on the server and control a bunch of fixed form factors. This is particularly also interesting where operators do see a need to have port densities above and beyond what fixed form factor routers support, which is around at 9600 gig ports. If you see a need to go beyond that, it's extremely easy to stack them up and move it onto the server. And now you have one control plane controlling a bunch of those boxes and routers. Because the control plane scales out in terms of memory and CPU at each protocol level, it's relatively easy for us to virtualize it and run it as one control plane, yeah? So I talked about our data store, and I did say that the data store connects to our own on-box real-time streaming telemetry agent, and it streams out the data that's there on the box. The kind of data that it streams out is all the ephemeral data that is there on the box running across for each and every software component that's there on the box. Now, if operator comes and tells us, hey, look, we've got the entire telemetry architecture in place. We just need to drop our own daemon or a software on your box or a switch, and would like to connect to your routing environment, start pulling data out and stream it to some place in a cloud or in our network that we have already set it up. We provide them with our Datastore SDK, fairly easy to integrate. They can integrate it, get into our environment, start pulling the data out, and stream it as and how they would want. If the operator comes and says, I've already set up a network for telemetry, and it's JSON or GNMI based, then we would simply ask them to use our on-box telemetry agent and stream it out. And if the operator comes and says, look, I've got nothing, I'd like to set something up, then we have a cloud-based analytics platform that can reside on-prem or off-prem, depending on what operator would like. And it's basically a platform that consists of a bunch of Kafka collectors, bunch of time series databases, dashboards, and it is designed to handle scale, data at scale, that could start collecting the data from Arrcus boxes, be it routers or switches, right? If you enable it, the kind of stuff you will get from routers or a switch platform is memory as well as CPU utilizations. You do not have to track this on the box at all. It's streamed out for each and every process that's running on the box. You could also track all the peripherals related information. We call this as part of the device insights. You can track everything that's running inside the box. You do not have to write single script. It's been monitored using the cloud platform. You could also check our serviceability dashboard, wherein it tells you what kind of profile the box has, what kind of system does it run, what image does it run. So gone are the days if an operator wants to say, I've deployed 300 of these boxes, I need to know what software version runs where, and I need to keep track of all that. That's all gone. You can use this platform to track it. Interface statistics are also tracked out. Any errors, everything has been brought out. Topologies for routing protocols. BGP as an example, you could do the same with ISIS that we support. It also tracks what AS numbers and on what boxes have you configured. Are these Arrcus boxes or third-party boxes? You can track all of that.
The blue boxes there, small blue blocks, are Arrcus. And I know the color probably from far you can't tell, but the orange ones are third-party non-Arrcus platforms. So essentially, you're blowing up that previous picture's AS and seeing what the nodes are within that.
So you could track all of this. You do not have to write any scripts. Actually, what it does provide also is a feedback mechanism. If you need to set an event and say that, hey, my route statistics or my BGP routes have gone beyond this number and I would like to be notified, the event mechanism is in place. It'll either log it on the system or send you an email if that's your preference, and you could set it up and get a feedback mechanism also. So the whole point here is, like I said, it's a platform. One of the applications, aside from all the statistics we provide that Murli talked earlier about, was the route origin validation. We provide this as an application. The operators are more than welcome to develop more applications that they seem to need for their network based on the data that they have collected.
So, question on that, on the BGP example that you had. Are you gathering that data by looking at the configuration and how it's in operation, or NetFlow, or how are you getting the intra-AS information into a visual?
Configuration, as well as anything that runs also on the box. Like I said earlier, we stream everything within BGP and routing protocols that are in there out to the telemetry platform. So they have configs. They also have what AS numbers that they got from the neighbors, what are the neighbors they peer with, and so forth and so on.
That's all operator defined as well. Sorry.
Gotcha. And this is an application that runs somewhere on an x86 platform.
Yes.
That is working with the control plane.
Yes.
It could also reside on box as well for certain use cases as well.
Gotcha.
So how long are you keeping the historical data for? Can you go back?
You can keep it as long as possible because it's a time series database that we use. And we sort of let operators dictate that because that would be directly proportional to amount of data you want to collect and hold upon. You could do it as long as months if you like. If you're going to go more than that, then we have suggestions as to how many time series database that you want to deploy, how do you want to scale this out, so forth and so on.
We also give kind of boundary conditions on each sort of multiple tiers, say 1 week worth of data. What kind of requirements do you have? If it's 1 month, how much do you need? Things like that as well. So there are boundary conditions and recommendations we have.
Along that same line, are there conditions as far as either archiving or moving things off that?
Yes,
okay.
Absolutely.
Yep.
It's a good point.
Good. Any more questions? I think that was my last slide. One more. So I want to talk about, we talked about operating systems. We talked about how the operating system sits and runs. It's a one OS, one architecture on switch as well as router. We talked about an ArcIQ system. I want to talk about the quality and reliability process that we have gone through in building this OS, right? From an architecture standpoint, we started off with first principles. A lot of code has been written from scratch. We want to make sure that the architecture is set right and it's deployed right. From coding tools perspective, as we write some of this code, we use newer generation tools to actually validate as we are starting to develop it. For example, we use Wellgrind, we use Coverity for static analysis. Any kinds of profiling that needs to be done is already built in our make system so that every little piece of code you write, you have a real-time view of either you're leaking a memory or either you're using a CPU more than it's needed, so forth and so on. That discipline and the check that goes into coding happens right as you code. Modern CI/CD based environment, we always do development of an EFT branch. We do not touch the master branch. Master branch is always stable. We have quarterly releases that come out. Only when the EFT branch is very well tested, we move the code into master branch as and when we are ready to release it, right? From a test and automation perspective, all tests for us are automated, so it allows our developers to write a piece of code, really test it, rather than writing a bulk of code and sending it to a test when you're done with bulk of code. So it lets you develop and test, if you will, and lets you fix anything that you find runtime, right? From a scale perspective, we have Xena and Ixia in place that we use to test our control plane, more specifically from a scaling and, of course, the data plane. Interoperability. Heavy on interoperability. We have tested the control plane extensively with all the well-known OEMs that are out there, various different platforms from these OEMs. We have also tested it against open source code that's out there. Of course, we do our conformance testing using Ixia, where all the RFCs are being tested and proven from a code perspective. And the code's already running on certain third-party or other internet, certain points in the internet exchange points without being talked about to make sure it's stable out there. It pairs with the routers and switches as well. We've also tested the optics from our perspective, that particularly the ones that we support and advocate to our customers. And finally, the code's actually deployed in production.
So I've got a question for you on interoperability. You've got Cisco and Juniper, very standard vendors up there. Are you guys going to be expanding into other, especially in the carrier space, other vendors, getting to things like Nokia, Ericsson, Metaswitch, things that are very common to find in layer 3 in the carrier space?
Yep, for sure, as and when that time comes along, absolutely. But I think covering Cisco, and the reason to cover Cisco and Juniper, and again, Arista to a great extent, is that between three of them, I think it's not to put Nokia out, but if you would have covered between 4 of them, any 3 of them, you would pretty much be conformant to the remaining ones.
And there's also, I think there's a question that came in from Twitter on the routing protocol support before you, and that came from Nick Baraglio, who's a field day delegate watching remotely. And he asked if you support BGP-LS and ISIS SR TLV.
We support BGP-LS. ISIS SR is
within a quarter.
Within a quarter.
Okay, gotcha. So you mentioned segment routing. So what segment routing are you supporting right now? Is that OSPF?
Node SID for BGP was supported day one. Adjacency SID is, again, scheduled to come by end of this year, and then ISIS SR.
Okay. Any plans for SRv6 or SRv6 Plus?
Yes.
Okay.
Early 2020, I would probably say.
Okay.
So effectively, the next wave, as you've seen, we've built multi-tenant fabrics with EVPN over VXLAN. We have the basic framework for providing a segment route transport layer today already is SRMPLS with BGP as the control plane, extending it to ISIS SR, and then extending the data plane options to SRv6 as we start seeing some customers' use cases, which we've already gotten. So all of them targeted towards that first quarter of next year.
And we probably should add a caveat saying we would probably support some of these things or these technologies for the silicon that has a support for it.
Yes.
Right.
SRv6 is a good example of that. It is dependent upon the silicon.
Sure, yeah, especially with the label depth and all of that, those concerns.